It sounds trite to say it, but our universe as we know it, as well as life on Earth, could not possibly exist without the quantum nature of reality. Here's how to make sense of that. At the heart of quantum physics are a few simple realizations. The first one is obvious, that if you break the stuff that the universe is made of down into its smallest indivisible components, you will arrive at what know as fundamental particles. These particles come in two main classes: fermions, which are half-integer spin particles, including quarks like the up and down quarks that make up protons and neutrons, charged leptons like the electron, and neutrinos, as well as their antiparticles, and bosons, which are integer spin particles, including the gluons which hold quarks together into bound states, like protons and neutrons, the photon, that is the quantum of light, the weak force bosons, and the Higgs boson. These particles all have their own intrinsic properties: masses, electric charges, color charges, weak hypercharge and weak isospin, and in the case of a great many of these particles, a finite lifetime, after which they will decay into more energetically favorable, that is, lower rest mass particles. The second aspect at the heart of quantum physics, however, is far less obvious. These particles, each and every one of them, doesn't come along with intrinsic properties that can be exactly known to arbitrary precision. Instead, there are several sets of physical properties that we think about as being inherent to a physical system in the macroscopic world, that are inherently uncertain, with many of those sharing a mutual uncertainty with other, equally important physical properties that can never be reduced below a certain limit. This intrinsic uncertainty is commonly known as Heisenberg uncertainty, and it exists between a variety of properties that we call conjugate variables in physics. The most common one that we encounter, illustrated above, is the uncertainty between a particle's position delta x and its momentum delta p. In practice as well as in principle, it's never possible to know, even with an ideal measurement, the exact value of a particle's position, that is, where it is at any moment in time, or its momentum, that is, how quickly it's moving in a particular direction at a particular moment in time. This isn't due to what we might think of as a measurement uncertainty, but rather it's an intrinsic quantum property of the universe itself. Moreover, the more precisely you measure one of them, delta x for example, the less precisely it's possible to simultaneously know the other, delta p, in this example. This isn't just true for position and momentum, but for all the conjugate variables we know of, including orientation and angular momentum, energy and time, a particle's spin in mutually perpendicular directions, electric potential and free electric charge, magnetic potential and free electric current, as well as several others that we haven't specifically mentioned here. It means more than just, oh, I can't know what the true value of these two quantities are at once. It means that when you measure one of them, the more precisely you measure it, the more you actually destroy any pre-existing information you may have had about the other one. The most illustrative experiment that I know of that shows this directly is the STERN-GERLACH experiment. The original experiment used silver atoms, but you can do it with any fermion, such as an electron, a spin, one-hove particle. All you do is pass this particle through a magnetic field, and because that magnetic field points in a specific direction, a beam of particles will split into two when it encounters the magnetic field. The particles that happen to be oriented with a spin of +1/2 in the direction of the magnetic field will deflect positively, aligned with that field, while the particles that are oriented with a spin of 1/2 opposite to the direction of the magnetic field will deflect negatively or anti-aligned with that field. Big deal, you say? Well, it's a giant deal because of this. Now let's say you want to know what this particle's spin is in a different perpendicular direction. In other words, let's say your first magnetic field was oriented in the z direction and the deflected particles split, half up and half down, in that z direction. Now you go ahead and set up a second magnet that's oriented perpendicular to the first, one whose field points along the x direction. What's going to happen? Sure, half the particles will deflect in the +x direction, while the other half will deflect in the x direction, just as you'd expect. But the messed up thing is this: you've now destroyed any knowledge of their orientation in the previous z direction. If you put a third magnetic field in place back in the z direction, the particles will split again, as though they have no memory of the first splitting, because they experienced a later interaction that wiped out that prior information. There are other bizarre quantum experiments that reveal these unintuitive properties of our reality, such as the double slit experiment, the quantum eraser experiment, the Mossbauer effect, and many others. But at the heart of it all is a fundamental truth of quantum physics, one that makes people very uncomfortable. Matter, although we visualize it as being made of particles, does not exhibit particle-like behavior except under one set of circumstances, whenever there's an interaction with another quantum particle. Exchanging another quantum with each other, colliding with one another, or absorbing one another, with some specific amount of energy involved in that interaction. This, right here, is the key insight of quantum physics, and the most complicated aspect of it that anyone attempting to make sense of it has to reckon with. Quanta interact like particles, with specific properties that can be measured down to the quantum limit of fundamental uncertainty, when they collide with or absorb one another, or even when they simply deflect one another by exchanging other quanta between them. However, when a quantum propagates, or simply doesn't interact with any other quantum, it behaves like a wave. This means if you do something like put a single quantum particle in a box, and you ask the seemingly mundane question of, where is the particle? You won't ever get a single location within the box as the answer. Instead, you can only get a probability distribution based on the properties of the particle and the environmental conditions set by the boundaries of the box for where the particle is at any moment in time. It's important to note that these insights about the nature of our quantum reality are agnostic about the interpretation one chooses. In all interpretations of quantum mechanics, these limitations for what we can know, what we can determine, and how quanta behave in the absence of an interaction are identical. Think about this two-sided nature of reality. When quantum particles propagate freely, they behave as waves, and when they interact with other quanta, their interactions force them to behave like particles. This plays a role in the macroscopic world as well. For example, in the double slit experiment. It's well known that if you take a wave, such as a water wave in a tank, and allow it to propagate until it reaches a barrier with two slits in it, the waves will strike the barrier, propagating through the slits, where they'll make circular waveform patterns that propagate outward, interfering with one another, and producing that very same interference pattern on a screen places on the opposite side of the tank. This works for quanta too: light, electrons, atomic nuclei, etc. Fire them at a barrier with two narrowly spaced slits in them, and that interference pattern is what we'll see. This remains true even if you don't fire multiple quanta at once, but rather individual quanta one at a time. However, if you try and observe which slit did each quantum go through, by causing an interaction with another quantum at each of the slits, the very act of forcing that interaction will destroy the wave-like pattern and will cause your experiment to reveal particle-like behavior instead. Just two piles on the opposite side of the barrier, corresponding to quanta that went through slit 1 and slit 2, respectively. In other words, we can experimentally confirm this picture. Quanta propagate like waves unless and until they interact with another one, in which case they behave as particles. However, perhaps the most profound place where quantum physics plays a role in our everyday lives lies in the greatest source of energy planet Earth has ever encountered: the Sun. Inside the Sun, the various atomic nuclei and electrons inside zip around at tremendous speeds, as determined by their kinetic energy at the temperatures present inside the core, between 4 million and 15 million K, from the outer edges of the core to the very center of the Sun. At these temperatures, we can calculate a probability distribution for each of the particles inside the Sun, including for the most important particle present there of all, bare protons. Sure, there are plenty of other everyday effects that are inherently quantum. The LED lights on your smartphone or computer screen that require electrons to fall into specific energy states. The photoelectric effect, that is the core technology lying inside every solar panel. The functioning of MRI machines relies on the quantum effect of nuclear magnetic resonance, and even the basic biological process of photosynthesis through chlorophyll molecules is quantum in nature. If you can remember just one aspect of quantum physics, however, take away this. All the various quanta in the universe may interact like particles, but they propagate like waves, including by overlapping, by superimposing atop one another, and by interfering. Once you understand that everything that exists has wave-like properties, you've begun to accept the most important, and arguably the weirdest, aspect of our quantum universe.